application of molecular symmetry and group theory topic is very important nowadays in the field of sciences, particularly in the field of chemistry. It has large number of applications such as, and these beside this there are large number of many more applications of this molecular symmetry and group theory in chemistry. Now, I will go for the procedure how to introduce this subject of molecular symmetry and group theory to the learners in the beginning. Now, first show some figures and ask whether these are symmetrical or non-symmetrical. This will give some idea about the symmetry of the molecules. Then tell about symmetry around us, and with that give some examples. Then give the examples of symmetry in nature, symmetry in animals, symmetry in architectures, and so on. After that, it is very important in dealing with the molecular symmetry and group theory, the shapes, oblique geometries of the molecule must be very clear to the beginners who is dealing with this subject. For this, take the help of the ball and stick model or tell innovative way of making models of their own with the help of clays of different color, or take colored small balloons. Use VSEPR theory for the shapes of the molecule. Now, let us take the bent molecule like this, and we can give various types of, say, this type of rotation into this molecule like this, or we can have some reflections into this. Later on you will learn in this field of this. We can take the example of the molecule like this one, pyramidal molecule, like we can take ammonia or some other molecule which has these shapes. We can give a rotation and number of other reflections thus are possible into this molecule. We take the tetrahedral molecule like in this over here, and we can rotate the molecule like this, or we can rotate the molecule like this. Like this we can have number of rotations, oblique reflections in this molecule. Now, let us take trigonal bipyramid molecule, and we can have this, hold this molecule along this axis, and we can give the rotation in this molecule, or we can take this and give the rotation like in this molecule. Let us take pyramidal molecule like ammonia molecule over here, or some other molecule you can take it. You can rotate this molecule around this axis, or we can have number of reflections into these molecules. With all these you will learn later on in your these modules. Let us take tetrahedral molecule like this. We can have number of rotation into this molecule like this, or we can give a rotation like this. We can have number of planes in this molecule. Now, then we can take the example of this pyramidal molecule, trigonal pyramid molecule. We can give a rotation along this axial axis. We can give this type of C2 rotation along this axis. Like this molecule also has large number of other symmetry elements. Now, let us take octahedral molecule and show the presence of C3 axis in this octahedral molecule. Generally, it is very difficult to visualize this C3 axis into this molecule. Now, this octahedral molecule which I am showing over here, we can give a number of rotation in this molecule like this one, or we can take this and rotate it like this. So, we can have number of rotation in this molecule. Now, I want to just show the presence of C3 axis in this molecule. For this, let us take a cube and then an octahedron. I inscribe octahedron into this cube, and then C3 axis passes from this upper corner of this cube to this corner of this, and It passes through the middle of this face and comes out from this. So like this you can show the presence of C3 axis in the octahedral molecule. Wherever there is a doubt, take the help of the models and try to explain with the help of the model. Most of the students, they generally confuse with these two terms, symmetry elements and symmetry operations. These have been clearly explained in the coming modules of this topic. After studying this module, you shall be able to know the concept of symmetry, define symmetry elements, know the type of symmetry elements, define symmetry operations, distinguish clearly between symmetry elements and symmetry operations, identified the symmetry elements in molecules, and perform the symmetry operation on the molecule. The concept of symmetry. Symmetry is an important concept in chemistry. Firm understanding of this concept of the symmetry and group theory is extremely useful in dealing with molecular structures, stereochemistry, spectroscopy, and reaction mechanism. The concept of symmetry is important to almost every aspect of life in our universe. The principle of symmetry plays an important role in modern science. The idea of symmetry principle originally resulted from the study of geometrical forms and observation of natural objects. There are countless examples of symmetry in nature. Symmetry principle finds lot of application in natural science, that is physics, chemistry, wherever geometrical properties are generally taken into account. The dictionary, Oxford Dictionary, English Dictionary gives the following two definitions of symmetry. Number one, mutual relation of the parts of something in respect of magnitude, a position, relative measurement, and arrangement of parts. Proportion, due or just proportion harmony of parts with each other, and whole, fitting, regular or balanced arrangement of relation of parts. Elements, the condition or quality of being well proportional or balanced. The first symmetry definition clearly has more scientific importance. The concept of symmetry sounds simple and familiar, yet symmetry is far more complex and difficult to apply in practice than one might think. Let us introduce the concept of symmetry in molecular system in a quantitative manner. The symmetry of the molecule is determined by the existence of symmetry elements about which symmetry operations are performed. To understand the concept of symmetry, let us examine the following figures.
Let us begin by asking the question that out of these figures, which is more symmetrical, x, y, or z? How many lines you can draw in the figure x, y, z so that the figure looks symmetrical about these lines? Your answer will be that y is symmetrical about one dotted line and z has two such lines about which the figure is symmetrical. Let us take an unlabeled square piece of card and rotate this by 90 degrees. As can be seen, we will get back the same figure. More successive rotations by 90 degree each time give rise to 180, 270 and 360 degree rotations about the dotted line perpendicular to the plane of the paper. These also give rise to similar results. Here, we can see that all the resulting configurations look the same and cannot be distinguished from each other. These rotations or movements are symmetry operations. Let us now carry out the rotations, but this time in labeled square planar cards. If we label the four corners as A, B, C and D, then it is possible to observe the effects of these movements or rotations. Let us carry out 90-degree rotation as shown here. We can see that after 90-degree rotation, we do not get identical or equivalent configuration. Continuing with successive 90-degree rotation, we get configuration 1 change to 2, to 3, to 4, and then 5. Note that out of all of these, only configuration 5 is identical to configuration 1. These rotations or movements are not truly symmetry operations.
Let us now further explain what we mean by the symmetry or symmetry concept. For this, let us take figure 4. In figure 4,
Now, if we rotate the figure shown around the vertical dotted line by 180-degree clockwise, the two figures can be differentiated after rotation because the hands are identified by letters. But if we remove the labeling, the figures will be identical or indistinguishable.
now concept of symmetry is familiar one, and generally one speaks of a shape as being symmetrical and unsymmetrical, even more symmetrical than some other shapes. For example,
To understand the concept of symmetry, we can examine the figures shown. First, we label the corners of triangles as X, Y, and Z, and then a dotted line is drawn in the plane of the paper through the vertex X such that it bisects the side YZ at P. In triangle A, the triangles XZP and triangle XPY are equivalent to each other. After rotating through 180 degrees, triangles A and A' are distinguishable. Hence, the rotation is not a symmetry rotation. If the corners of triangle A are not labeled, we will not be able to distinguish A from A'. In that case, the rotation will be a symmetry rotation. But in triangle B, the interior angles are not equal. Hence, after rotation, we can distinguish between triangles B and B'. Thus, triangle A is more symmetrical than triangle B about the dotted line in the plane of the paper.
let us go a point further. I take the triangle A again, and now instead of taking the vertical line I passing through x and dividing by z, I take now a line, imaginary axis, passing through the mid point of this x, z, y plane as shown, and give clockwise rotation to this figure, that is 120-degree. Now, after first 120-degree, you will find y moves to x, x moves to y, z, and z moves to y. That is, all the corners are interchanged, and still figure looks equivalent if the corners are not labeled. Let us go further 120-degree rotation. Here now y moves, and then x also moves, and z also moves, that is, corners are again changed. Let us go the third 120-degree rotation, and in this what you find, after this 120-degree rotation, I am reaching to a configuration 4, which is identical to configuration 1. So, it means the configuration 1 and 4 are identical. Now, if I do not label the corners of this triangle, then the configuration 1, 2, 3 and 4 all are identical, and 120-degree movement of this triangle about vertical line is a symmetry movement, or you can say it is a symmetry operation.
After successive 120-degree rotations on triangle A,
The configurations 1 and 4 are indistinguishable even when the vertices are labeled. In these types of rotations or operations, we had an imaginary line running perpendicular to the plane of the triangle. The rotations were performed about this line. Since at the end of the operation we get indistinguishable configurations, these imaginary lines and physical movements or rotations or operations are special.
Now let us define symmetry elements and symmetry operation, and let us try to make a distinction between these two terms. Symmetry elements and symmetry operations are closely related terms. Symmetry operations should not be confused with symmetry elements. The difference between these two terms has been explained in these modules properly. Now, let us first define and then we will go with this. Symmetry element, it is an imaginary geometrical entity, that is a point, a line, a plane as shown in the figure, about which symmetric movements are carried out, that is a point, a line, a plane. And symmetry operation, it is actually the physical movement, or you can say rotation of the body of the object around an imaginary point or a line or a plane in such a manner that after the movement the final configuration of the object is indistinguished from the original configuration of the object. The symmetry elements and symmetry operations are complementary to each other. If a symmetry element exists in an object, then there must exist a symmetry operation about the symmetry elements, and if there exists a symmetry operation, it must be about in already existed symmetry elements. That is, you cannot separate these two terms from each other. Existence of one demands the existence of other. Symmetry elements are imaginary, as pointed earlier, point, line and plane, while symmetry operation are the actual movement around which these operations are carried out. Types of symmetry elements. Discussion shall be restricted to the symmetry elements present in isolated molecules, that is, I will deal with the molecular symmetry. Before discussing the type of symmetry elements, let us discuss their naming system. Commonly, there are two types of naming system, and these are Schoenflies notation and used widely for molecules and spectroscopists. Then there is a Hermann-Mauguin or international notation generally used by crystallographer. In this module, I shall make use of the Schoenflies notation and in dealing with the molecular symmetry. The types of symmetry elements that may commonly present or observed in the molecules have been summarized. The first symmetry elements is the identity symmetry elements. Its symbol is E and operation moment is C1, rotation by 360 degree, or you can say do not do anything on this. C1 means cyclic rotation by 360 degree, or indirectly you can say in this object we do not have any symmetry elements present. So, presence of identity demands the existence of the object. Now, the second symmetry element, the symmetry axis or proper axis of rotation, is symbol given is Cn. C means cyclic, N means the number of time the operation can be carried out so that I can reach to the original position, or even you can say order of the group. Now, what we do in this rotation action, we rotate the object about the imaginary axis. Now, then third symmetry element is the reflection plane or mirror plane or plane of symmetry. Symbol is sigma. And in this what we do? We put a plane in the middle of the object and then reflect one part of this to the other part of the molecule and then see whether this matches or not. Fourth symmetry element is the center of symmetry or point of symmetry or inversion center. Its symbol is I. Inversion, the operation done is inversion through a point. Through a point is nothing but through the origin generally. Now the fifth symmetry elements, improper axis of rotation or alternate axis of rotation. Symbol given is Sn. Now in this symmetry elements, it is a combination of two symmetry element, symmetry operation, rotation about a symmetry axis followed by reflection in a plane which is perpendicular to rotation axis. That is Sn axis is a combination of rotation axis followed by a reflection in plane perpendicular to this rotation axis. So in the molecule we will have identity, proper axis of rotation, reflection plane, center of inversion or Sn axis of rotation. Let us take the fifth symmetry elements. Actually this is not a, I can say, isolated symmetry elements or imaginary symmetry elements. It is the combination of two symmetry elements, that is rotation axis, then reflection perpendicular in perpendicular plane to this rotation axis. And what we do in this symmetry Sn axis rotation or operation, that is we carried out a certain rotation about a rotation axis followed by a reflection in a plane perpendicular to this rotation axis. So this is a Sn axis. So total in this symmetry elements that are present or expected are I, Cn, sigma, I and Sn. And in isolated molecule we generally deal with this type of symmetry elements. Now let us explain each and every symmetry elements that is present into the molecule, what it means. Presence of identity symmetry element means that object exists. To perform an identity operation, rotate the object through 360 degree about a randomly chosen axis or do nothing to this object. Even though it makes no sense to have such a symmetry elements, but the concept or you can say postulate or conditions of group requires the existence of a neutral element or identity element. The asymmetric molecules like bromochlorofluoroethane, methane have identity symmetry element only. Rotation through 360 degree about any chosen axis is represented as Cn, and Cn and rotation, symbol C stands for cyclic rotation, C1 is the Schoenfly symbol, and if I give the capital I, it is the Hermann-Magon symbol for identity. Beside other symmetry elements, every molecule possesses these symmetry elements. A single rotation through 360 brings the whole molecule to original configuration and end each and every point at its original place. Therefore, only one operation is required to reach the original positions. Identity is vital in the correct mathematical description of symmetry by group theory. In Cartesian coordinate system, identity symmetry operation E on a point x, y, z1 can be shown, that is, if I take a point x1, y1, z1 and perform a clockwise 360 degree rotation, I will reach again to the same point x1, y1, z1 as if I have done nothing. So this 360-degree rotation, if I reach to the original position, it is an identity and no other symmetry are present. Another important point, reciprocal of a symmetry element or symmetry operation. Now, identity is the operation. So, what is the reciprocal of a symmetry operation? Is the symmetry operation of the same type which can bring the object back to its original configuration. That is the identity situation. Reciprocal of a symmetry operation can be represented by putting an inverse sign over the symbol of the symmetry operation. Inverse E can be written as E raised to the power minus 1. What is the reciprocal of E? If question asks us, since in identity operation we do not do anything or we just simply rotate by 360. So, what will be the reciprocal of the identity? It is E inverse is nothing but E. That is, either you rotate through 60 degree or do not do anything, you will have the same. So, E inverse is equal to E, that is E symmetry operation does not do any change in the molecule. Now, let us take some examples of molecules which have identity E only, that is no other symmetry elements. Let us take the example of FnHCl molecule. It is a pyramidal molecule. You try to put any mirror plane or any axis, it does not have any symmetry elements. Take the molecule second, that is CFHClBrH. In this also you try to find it out, there is no symmetry element except a 360-degree rotation will bring back this molecule to the original. You take the silicon compound number third, again it is similar to the carbon compound and it does not also have any symmetry elements present into this molecule. Now, if I take the second molecule and give a 360-degree rotation to this molecule, it will be give me again identical molecule, and these molecules, these types of molecules, they are mirror image to each other. Now, in this module, what we have learned so far? We have learned how to define symmetry elements and symmetry operations, and also try to explain the clear distinction between symmetry elements and symmetry operations. Also, we have taken the Schoenflies notation for these symmetry elements. 5 symmetry elements have been pointed out, and also we have taken the concept of symmetry in this module. Now, meaning of identity symmetry elements has been defined and number of examples have been discussed.